We have a compounding investment, and Jessica wants to know how long it will take for an initial investment of $1,000 to double in value. She tries this equation, and we're given that R is the rate of return as a percentage, and D is the time the investment would take to double in value in years. So part 1 is, alright, in 11 years we know it will double, so what is the rate of return? So again, we're given this equation up here, this formula, that relates the rate of return to the time it would take to double. And we are given the time it will take to double, so we can work out the rate of return. Right, time it will take to double D in years is 11. And now we can work out what the rate of return is as a percentage. So we could just start by substituting in D equals 11. So 2,000 equals 1,000 brackets 1 plus the rate of return, which is what we're looking for, over 100, all to the power of 11. So now we just need to solve for the unknown. So we could divide both sides by 1,000. Right, to eliminate this 1,000 here. So 2,000 divided by 1,000 is 2. 1,000 divided by 1,000 is 1. So I don't need to write that. I'm left with 1 plus R over 100 to the power of 11. Great. Now we can take the 11th root of both sides. So the 11th root of 2 equals the 11th root of something to the power of 11. So we're just left with what's inside the bracket. Now we can subtract 1. So the 11th root of 2 minus 1 equals R over 100. Finally, times by 100. And so like at this stage here, the 11th root of 2, I don't know that in my head. I would have just put that in my calculator. Again, you could get down to here and then just put that whole thing in your calculator. And we're left with R should equal 6.5%. Okay, so the rate of return is 6.5% for the value to double from 1,000 to 2,000. In part 2, we're asked to rearrange that formula and make D the subject. And we're actually given what the answer should look like. So if our answer is a little bit different, we need to manipulate it to match the ones that is given to us. But for these types of problem, I just like to tackle it and just try to rearrange it myself. And then if I'm a little bit off, I might be able to see what I need to adjust, or maybe I need to use another log law to simplify it a little bit further. So let's just write out the equation. Right, we could divide both sides by 1,000 like we did last time. So 2 equals 1 plus R over 100 to the power of D. And now at this point, in the last question when we were solving for R, we took the 11th root right? Because d was 11, but here d is just an unknown. So instead of taking the root like that, we could take the log of both sides, technically of base d, but we don't need to write that. Log base d again of 1 plus r over 100 to the power of d. So since we did it to both sides, the equation still holds. Now using our log laws, we know if we have a power in the log, we can bring it out into the numerator, like multiplying out the front. So we can write that as d times log brackets 1 plus r over 100. Right, so I just took the exponent, took the power, multiplied it out the front. So that's a log law. And now from here you should be saying, alright, let's just rearrange for d in one more step. So d equals log 2 divided by this log. Log 2 divided by log 1 plus r over 100. And that's exactly what they wanted us to find. Alright, now part 3. She's found an approximate rule, rule of 72. And she wants to find out how close they are, the approximate rule and the more rigorous rule in the previous questions. So show clearly that the value of r for which the rule of 72 exactly calculates d is the solution to this equation. That said, we do not need to solve the equation. So for it to exactly calculate d, that is saying that this approximate d must equal this d exactly. And what that is saying is that 72 divided by r must equal this log expression. So our first step should be to equate those together. 72r equals log of 2 over log 1 plus r over 100. Alright, so that specifies that the approximate rule, the value for d that the approximate rule calculates, is the same as the one, the expression that we just rearranged for in part 2. Now what's a little bit odd is they're saying that that is the solution to this equation. So how do we go from here to here? You'll notice, what do we have? We have r as a power there. There's no logs. There's a power of 72. So that's telling me that we need to take this log expression and convert it to its exponential equivalent, which should boil down to this. Cool. So to do that, let's get any logs out of the denominator, because that's just messy and hard to deal with. So we could bring log of 1 plus r over 100 to the left hand side, and while we're at it we could just bring r to the right hand side. Alright, so cross multiply essentially. 72 times log 1 plus r over 100 equals r times log 2. Right, so I just got rid of the denominators. That's fine. Now we can start using our log laws. Alright, before we can convert a log to an exponential, we need the argument. We need everything in the argument of the log, like in this bit here. Right now we have something multiplied out the front, but we could use the log law to bring that into the power. So log 1 plus r over 100 to the power of 72. Notice that's actually already looking like this term up here. And we can do the same with the right hand side. Bring the r into the power. Log of 2 to the power of r. That's starting to look like this term here. And since we have logs on both sides, we could do the exponential of both sides to eliminate the logs. So that becomes 1 plus r over 100 to the power of 72 equals 2 to the power of r. And we're not dividing by log, because log is a function. What we're doing is we're taking the inverse function on both sides, which kind of is like divide when we have, let's say, 2x and like 4x. It's kind of like dividing by 2, right? We're undoing the multiply, but here instead of dividing, we're using the exponential function, which is the inverse of the log function. Alright, and now our last step, try and make it look like that equation. So we could do 2 to the power of r and subtract 1 plus r over 100 to the power of 72 equals 0. So to recap this one, we equated these two expressions, so 72 over r to this log expression, rearranged it, converted it to its exponential form, and then finally rearranged to get to this equation.